I want to talk today just for a few minutes about the chemistry of what we're going to do in this lab. And then we're going to get back into chapter 14. And we're going to make some big progress today in chapter 14. And then I'll give you the last 20 minutes or so of class just to work. Remember, you have the lab on the lab on the colors, the rainbow. That is due on Thursday. So what we'll do on Thursday is we'll get here and we'll take about 15 minutes or 20 minutes. We'll continue in 14, but then the rest of the time will be on the lab, this lab. But by the end of the period, you're going to need to turn in the rainbow lab. So if you have questions today, I will, if you have questions on that lab, I'll be able to help you. And I will be here today too during access. So if you want to come in during access, you can. Okay, so this is the point in the lab. The title is an acid-base titration. And of all experiments done in science, this is the one that may be the most commonly done one, is an acid-base titration. I'll talk about the procedure. We're going to have these long, skinny tubes, which you can see on the handout. I actually got them out back there behind Tyler. We'll be all ready to go. Or we'll talk about the procedure of this for the titration. And the purpose, there's two parts to this. The first thing, and I want to talk a little bit about how we're going to do this just from a chemistry standpoint, is to determine the concentration of the HCl solution. So you're going to make an NaOH solution. I'm going to talk about it in a second. And then you're going to use that. And the titration, simply defined, is an experiment where you have a solution with a known concentration. In this case, that is going to be the NaOH. You're going to make it a certain concentration. I'll show you that, to find the concentration of an unknown solution. And so we're going to use that in this lab to find the concentration of an HCl solution. That's going to be the first part of the lab. And the second part is we're going to determine the molar mass of citric acid. And of course, we can get it up on our phones and we could just Google citric acid and boom, we can see the molar mass. But we're going to do it experimentally, and I want to talk about that. And then if we put the purpose in the form of a question, this is what we're setting out to do. So we're going to find the molarity of the HCl solution, number one, and then we're going to find the molar mass of citric acid solution. Okay, so this is how the chemistry of what we're going to do here. So in part one, this is kind of and first of all, one thing you should know, if you look on the pre-lab question one, so on this, the very front, this is one thing you guys would be really good to have done when you get here on Thursday. Does anybody not get these? Mike, did you get these handouts? You got them? Everybody's got them. So what you should do is calculate. You're just going to use the old molarity triangle to find the mass of NaOH needed to prepare 150 milliliters of a 0.150 molar solution. So you should do that one, because if you look on this page, here's the titration apparatus. This is, and again, I'll get this out tomorrow, but if you look on the back, this is the procedure. And the very first one, and actually there's a mistake. So if you look on this one, it says mass out approximately enough solid to make 100 milliliters. You should cross out the 100 mils, and you should write in 150 of a 0.150 molar solution. So on this handout on the back, the very first sentence there, which now means it's exactly like number one here. And so that's, when you guys get here, that would be really good to have done for class on Thursday, to know that mass, and that's where you're going to start. And again, I'll talk about the procedure, but here's the chemistry of what we're going to do. So in part one, this is kind of the fancy chemistry way to do it, which I think is probably the best way, but there's an easier way to do this. So this is going to be our reaction. Okay, this is going to be, as we go further and further into chapter 14, we're going to write reactions. You know what you get off here? You know what you get off here? HCl plus NaOH, acid-base reaction. What do you always get off in acid-base?
Water and salt.
You get off water and salt. So it's the outers and the inners. So the outers are H2O, the inners are NaCl. Okay, so here's kind of the fancy official way to do it. What we're trying to do is we're trying to find the concentration. That means the molarity of the HCl. Well, molarity is moles per liter. Okay, so we're going to try, and I kind of look at both parts. It's kind of like an equation where we have plug and chug. So here we have moles over liters. This is going to be in the data table. This you guys are going to measure with these long, skinny things called burettes, and I'll talk about that on Thursday. Well, this, we're going to make this 1.5 molarity. And again, you're going to know, I shouldn't say question mark, these liters are going to be from the data table. So to find the molarity of this, I got to know moles or liters. Well, I know the liters from the data table. The trick will be to find the moles. Well, what I can do is I can find the moles of the NaOH by doing molarity times liters. So I've got the molarity, I've got the liters. And so once I know the moles of the NaOH, what I'm trying to find is the moles of HCl. So it's going to be 1 mole of NaOH for 1 mole of HCl. That'll give me moles of HCl. I'll take that and I'll put that right there. Now again, that's kind of the longer way to do it, but that's really kind of a more official way to do it. But another way you can do this is the old the neutralization equation. We should get the same answer. So Ma, molarity of the acid, volume of the acid, the number of H's, Mb, molarity of the base, volume of the base, and the number of OHs. Okay, so we can use that. Well, the molarity of the acid is X. This is in the data table. This will be the volume. The number of H's are 1 because it's HCl, 1. The molarity of the base, we're going to make it. This is the one question I want you guys to do for class is you're going to make it 0.150 molar. This again is going to be in the data table, and the number of OHs are 1. And if you do it this way, that's fine with me. As a matter of fact, I think on the AP test, if it's a neutralization problem, and you do that, you're going to get the right answer. So again, this is kind of the more kind of a fancy official stoichiometry chemistry way. Get the same answer. Does that make sense? Does that make sense, Tyler? Yeah. Okay, so that's about this. Now, the second part of the lab is we're going to again use NaOH. And again, you can look up citric acid, but we're going to find it experimentally. And usually we get fairly good results. For this one, we've got to do this. I'm going to take this is the equation. And this is how I'm going to write H3A. If you look on the back of this handout, down here at the bottom, it says that the determination of the molar mass of an unknown triprotic acid. Citric acid is triprotic. And today I'm going to define that, but you could guess what that means. Triprotic means it's got 3 hydrogens. So again, I'm going to write out a reaction. Now this time, you have to use the stoichiometry way. Because we're not trying to figure out the concentration. We're trying to figure out the molar mass. The molar mass in this. And again, this is just the way in chemistry. Like if you looked on the formula sheet, like today I'm going to refer to the formula sheet some. If you look on the formula sheet, how a chemist, he or she typically writes in an acid, you can see it like right here under equilibrium, the third one, Ka, they write Ha. So they're just talking about any anion. So that's what I did here, but because it's triprotic, I had this. So we're trying to find the molar mass of this. This is the citric acid. Well, molar mass is grams over moles. So again, to me, it's like a plug and chug thing. It's like a plug and chug. So what I'm going to do is this, the grams are going to be right in the data table. I think it says, when you guys do this, down here on the bottom, determine the molar mass of citric acid by titrating 0.20 grams. So you're going to weigh out around 0.20 grams. So it's going to be in the data table. But the trick here is going to be to find the moles. Well, we're going to use this same thing that I was talking about up here. We're going to do the moles of the NaOH which is molarity times liters. I know the molarity. I'll know the liters from the data table. Now, this equation we're going to have to balance. Now, we're still going to get off water, but now the salt is the anion would have to have a charge of -3. H is a +1, +1, -1. So here, if I do this, I've got Na1, but A3. So what I get is Na3. Then I have to balance this. This time up here, everything's 1 to 1 to 1 to 1. That won't be the case here because of these 3's. So you'll know the moles of the NaOH. So once you know the moles of the NaOH, then you'll use the balanced equation. You'll have the moles of the NaOH for the moles of the citric acid. Again, you'll have to have the coefficients right. And again, you can look up the formula, but the point here is just to go through experimentally how you can find the molar mass. So this gives me the moles of the H3A. And then I'm going to take that and I'm going to put it right there. And typically on this, we usually get fairly decent results. I mean, you guys can Google it or you look it up. Obviously, we can easily do that. But we're going to go through it experimentally and determine that. So it might be a little confusing, but a lot of that stoichiometry, the molarity triangle we talked about before. I'll talk about the procedure part of this on Thursday, but hopefully you see a little bit of the picture of what's going on there. So, okay, then I want to leave that. We'll come back to that again on Thursday, but it would be really good to do pre-lab question 1 before you get to class on Thursday, so you know how much of that you're going to weigh out. And what we're going to do, one other thing on this is there's this point called the equivalence point, or really a lot of times the equivalence point and the end point, they're one and the same. They're technically different things. The end point is where the indicator changes color. The equivalence point is really what we're shooting for, and that's where the moles of the acid equal the moles of the base. And the indicator we're going to use is this indicator called phenolphthalein. And phenolphthalein turns pink in the presence of a base. And if you remember, I think it might have been, I think, last week when I had the 2 burettes over here by Jordan. Remember, I had a little bit, it turned pink, a little bit, it cleared up. Did I do that?
Yeah.
You want to get to that point. You had just a little bit, it turns, a little bit back, acid, it goes back clear. Phenolphthalein in an acid is usually clear, and in a base, it's a pinkish color. And when you get to that point, that's where you stop. And if you can get a light pink color, that is the best. So, okay, I'm going to leave that up for 1 more minute if you wanted to take a picture or copy it down. So you at least got an idea, hopefully a little bit, on the chemistry of what we're going to be doing in that lab. And again, the titration is, of all experiments that we do, that they do in science, that is probably the most common one. Okay, so now we're going to go back to chapter 14. And again, if we had time, in chapter 15, we would have done another titration. And in that one, we would have actually, I've got these digital pH meters, but we're not going to be able to do that. Do you have your computer, Lorik?
Yeah.
Could you just see if the notes are coming up? That's all I need. Just could you see if the notes are coming up on the Google Meet? Okay, so back where we left off. So what we were talking about, and thanks for being willing to do. I think it is. Hopefully it is. So again, we're going to go here for a while more into the heart of chapter 15 or 14, and definitely some new stuff today. And some stuff that's not that hard, which we would have covered. Is it up?
No, it's just you. It's recording though.
It's recorded, so that's a good thing. Present now. Is it up now? It is now. Okay, good. You can put it away. Thanks, Lon. Okay, so definitely go to some new places. Like I said, we're going to go here for a little bit. Then I'll stop and I'll give you guys a little bit of time to work on the lab. And if you have questions, I'm more than happy to help you with that. Okay, so this is where we left off. So we're going to write out the ionizing equation, and Ka goes back to the same K that we had back in chapter 13, which is equilibrium constant. The A just indicates that it is an acid. Okay, so, and I was telling my period 2 class here that if in writing, and this is something that we'll do more of, especially into next week, but writing equations, and for acids, you can really write in water as a reactant or not. The one time you absolutely have to include water as a reactant is when you have a weak base. But here you can or not. So let me show you. So what I'm talking about here, so I got NH4 positive. If I include water, which is okay, for an acid, doesn't matter, strong or weak acid, you can include water. I'll show you, or not. Either way is acceptable. So if this is the acid, this is the base. And I'm going to review today the strong acids. Okay, remember there's 6 strong acids. This was not one of them. So this is a weak acid double arrow. So this is going to give up an H. So we've got H3O positive. So this would be the Ca, the conjugate acid. Remember, a base has a conjugate acid. They differ by a single H, and the acid has a conjugate base. So this is going to be NH3. So this would be the conjugate base. And also remember, too, when something gains an H, its charge increases by 1. When something loses an H, its charge decreases by 1. So there's the ionization, just the equation of the dissociation. Now, then if I write out the Ka, so I have H3O positive times NH3. So the 2 products on top, and then NH4 on the bottom. And I don't include water because water is a liquid. Remember, solids and liquids are not included in the equation. Now, it's totally acceptable and fine for acids to not include water. So you could have done this. That would be fine. On our test, on our quiz, on the AP test, if you wrote this like this, it's totally fine. And then if I wrote the K expression, it would just be, and remember, H3O and H plus are interchangeable. They're one and the same. NH3 over NH4. Right.
If you write it without water, do you still need to double arrow?
Yeah, I should have had a double arrow. Yep, that was my mistake. Okay, let's do the next one. So I've got C6. So this one I'll do without water. Again, I could have done it with water or without. NH3 positive. So they're saying the Ka, that lowercase a up here, that lowercase a is a big clue that this is an acid. Okay, so this is going to act as an acid, so it's going to give up. It's going to give up an H, and so its charge is going to decrease by 1. Plus H plus. So all we're doing is showing this ionization, the breaking apart. And again, this should be a double arrow. You're right. And then the Ka, so the products on the top. And the reactants on the bottom. Again, this is something we're going to come back to later in this chapter, especially when we're writing reacting acids with bases. The last one's kind of confusing. So I've got Al H2O to the 6th, positive 3. This time I'll write it with water, but again, I don't have to really write it with water. I could have done it without water. Now this one's a little bit confusing, but remember acids, to be an acid, it has to have H. Later on today, I'm going to define amphiphilic, which means something that can act as an acid or a base. Well, to be amphiphilic, it has to have hydrogen, because it's got to be act as an acid, it's got to give up hydrogen. Okay, so watch what happens here. So one of these waters, one of the 6 is going to give up an H. So what we're going to have here is H3O positive. But then what happens here to this is that now it's H2O to the 5th. So one of those 6 waters gave up an H, and it was left with OH. And this would all now be +2. Because when something loses a hydrogen, its charge decreases by 1. Okay, then if I write the Ka, again, just the same thing, the equilibrium constant. So the product's on the top, so I've got H3O positive. Okay, so the product's on the top. And then what's on the bottom is this. Okay, so the whole point of this slide is simply to go back and just to review or to make sure we're good with writing equations for just the breaking apart the ionizing of an acid in water. Okay, next point. So the key thing on this slide, the key thing here is this right here, which I talked about a little bit yesterday. So strong acids yield weaker conjugate bases. A negative, so A negative is a conjugate base. It's the anion in an acid. Is a weaker base than water. And there's a couple things I'm going to write on the board here. That's the key thing there. And then here, a weak acid yields a stronger conjugate base. So the point is, and again, there's a couple little diagrams that are helpful for me that I'm going to write on the board here. But the conjugate acid of a strong base, or sorry, let me say that. The conjugate base of a strong acid is a weaker base of water. The conjugate base of a strong acid is a weaker base than water. And then the conjugate base of a weaker acid is a stronger base than water. So that's kind of what's important here. Again, what's key here is this. I'm going to erase the board here in a second. So you want something on the board a picture of it or finish it up. You always have a hard time saying that right, but the conjugate base of a strong acid is a weaker base than water. And the conjugate base of a weak acid is a stronger base than water. So if I list out here, just to review, the strong acids and their conjugate bases. Remember, there's 6 of them. These would be weaker bases than water, which means they're not going to be able to pull on hydrogens as strong as water. So here are the strong acids. So HCl, HBr, HI. Again, what I was telling you yesterday, how I always remember these is in the purple column. I'm pointing at the periodic table up there on the wall. The halogens, HCl, HBr, HI, and then acids that we've used in labs, nitric acid, sulfuric acid. And then the one that we've never used and we never will, which is the strongest acid, which is kind of the outlier, the unusual one, perchloric acid. Okay, so here are their conjugate bases. Cl negative, Br negative. All these bases would be weaker bases than water. And something that we're going to get to next week is when you put these bases in water, they're not going to be able to, the word is called hydrolyze. They're not going to be able to break water apart. Notice too what happens with sulfuric acid is it gives up just a single H. So it's HSO4, CO. Now, the list of weak acids would be hundreds upon hundreds of weak acids. These 6 strong acids, all the other are weak acids. But here, let's just look at a couple of them. So here's weak acids and their conjugate bases. These bases would be stronger than water. Bases are stronger bases in water. So kind of the example that chemistry teachers typically use for this is acetic acid. So for acetic acid, so this is, I always like to write acetic acid like this. I always like it because it shows that the H that it gives off. Some people write acetic acid like this. When you get into organic chemistry, a lot of people write it like this. They're one and the same. Well, it's conjugate. The reason I like it like this is I can see that conjugate base. So if I see acetate ion, it's a stronger base than water. Or here's HF. It's kind of this weird, unusual, strong, weak acid. So it's a weak acid, but it's a stronger weak acid. So it'd be F negative. And again, this is a new concept. This we did not talk about, even if you were following along in first year chem. Okay, and then this always helps me. I have this continuum then here. So if I have got H2O, so we're talking about bases here, and H3O here. So here are the strong acids. And here are the weak acids. And what that's saying is the strong acids are stronger acids than H3O. And H3O is a stronger acid than all the weak acids. Well, then up here, these would be weaker bases. if we're talking about their conjugate bases, the CB, the conjugate bases of the strong acids, these would be weaker bases than water. And these, the conjugate bases here, would be stronger bases in water. So kind of the dividing line for the bases are water, and for the acids is the hydronium. Okay, so then it can lead into a problem like this. You have to be given the table like this. Okay, so you're given this, the strongest acid. So how can you tell the strongest acid? Any thoughts? How can you tell the strongest acid? Jordan?
By the value of K.
By the value of K, right? And the larger the K, the stronger the acid. And you might want to note that, it's not in the notes. The larger the value for K, the stronger the acid. The larger the value for K, the stronger the acid. Or the smaller the value for K, the weaker the acid. Smaller the value for K, the weaker the acid. Okay, so then answering this question, what is the strongest acid? It would be whatever has the highest value for K. And that's actually a tie. I always look at these, when I have these numbers with exponents, the first thing I always look at is the exponents. So -2, -2, -3, -4. -2 is bigger than -3, which is bigger than -4. So actually the answer to this question would be the HSO4 and the HClO2, because they have the highest value for K and they're the same value. Okay, now this question, which has the strongest conjugate base? Well, that would be the weakest acid. What's the weakest acid on this table? So again, I keep looking at the exponents. Down here, all of these are -10. Which of these is the weakest? Which of these has the smallest number? It would be the phenol, right? It's the bottom one. Because if they're all -10, and then I look at the number, and then I go back to the number, this would be the smallest one. So which has the strongest conjugate base? It would be the weakest acid, which in this case would be phenol. Does that make sense? Okay, so then you have a question like this. So that's why this diagram is helpful here. So rank the following from the strongest to the weakest bases. Water is the dividing line. Okay, so water is stronger base than those bases that came from the strong acids. And then the bases that came from the weak acids are stronger than water. But then to distinguish those, we would go off the one that's from the weakest, the conjugate bases from the weakest acid would be the strongest conjugate base. So if I look at these, first of all, I see Cl, which is right here, okay, which means it came from a strong acid. So that means it would be the weakest of all the bases. Okay? Now, the F, the NO2, and the Cn, none of those came from here. So you really, this is why we got to have the list of the strong acids and the strong bases in your brain. So water. Okay, now to distinguish the F, the NO2, and the Cn, I go up here. So here's HF, 7.2 times 10 to the -4. Here's HNO2, 4.0 times 10 to the -4. And Cn is right here, 6.2 times 10 to the -10. So this is the weakest of all acids. What does that mean about its conjugate base? It's the strongest conjugate base. So this is going to be the strongest conjugate base. And then to distinguish between these two, Those two, both are 10 to the negative 4, but NO2 is a smaller number. So then it would be F negative, just a little bit stronger acid. So it's going to be a little bit weaker base. And then NO2 negative, and then finally CF. This is a topic we'll come back to later in the chapter, because what we're going to get to is we're going to look at salts. They don't even have H or OH in them. And we're going to decide, okay, is this acidic, basic, or neutral? We got to remember, okay, so if this cation came from a strong base, it's such a weak basic or weak acid in that case, it's not going to react with anything. And then we'll look at the anion and we'll say, okay, did this anion come from a strong or weak acid? So we will revisit that. Okay, and this just kind of analyzes this, and here are some problems. And again, you got the lab to be working on, but problems you can look at. But so for strong acids, the Ka is large, it goes far to the right. The H plus equals the acid, and the A negative, that's the conjugate base, is much weaker base than water. And then the weak acids, the Ka is small, so equilibrium is going to the left. The H plus is far less than the HA, but the conjugate base is much stronger than water. Okay, the next page just has a bunch of definitions on it, which are not like key things in this chapter, but there are things that we should be able to recognize what they mean. So I'm just going to put this up, talk about it briefly, then I'll go over and give you a second for those that are taking notes to write these down. But monoprotic means it gives off one H. Diprotic means it could give off two H's. In the lab, which I pre-labbed here at the beginning of class, that acid is triprotic, which is what this is going to be. Okay, so you guys can look at that. I'll talk about all this. I'll give you a minute for those that are taking notes. so let's just go through these definitions. So monoprotic again gives off, and you guys would have guessed this anyways, gives off one H. I always think it's confusing, and in first year chem, sometimes they get a really good question. They look at acetic acid and they go, wait, Mr. Wood, that has 4 H's. Well, really, the conjugate base is the acetate ion, and that 3 is part, that H3 is part of that. This is one reason why I like writing acetic acid like this. So really, it does have one ionizable H. Diprotic has 2 ionizable H's, so this H3PO4 would be triprotic, which, like on the lab, the citric acid is triprotic as well. It would give off 3 H's. An oxyacid is an acid in which the acidic hydrogen, so that would be the hydrogen that's given off when it dissolves in water, is attached to oxygen. Acetic acid is a good example of that. This is the hydrogen that's given off that's attached to oxygen. An organic acid contains carbon. Well, that acetic acid is a good example of that as well. An amphitheteric is a substance that can act as an acid or a base. Water is a great example of this. But it's got to have hydrogen in it. To act as an acid, it's got to have hydrogen. Like here, if you look at acetic acid plus ammonia, again, compare the reaction side to the product side. Well, here, the acetic acid is an acid. Compare here, there's its conjugate base. It's given up an H. And the NH3 is accepted, so this is a base, and there's its conjugate acid. But here, if we take acetic acid, and now we combine it with a strong acid, so look at what happened over here. The HCl is now acting as the acid. But here, the acetic acid is acting as a base. So a lot of times it depends as to what it combines with. Like here, because acetic acid is a weak acid, hydrochloric's a strong acid, the strong acid is going to win and act as an acid. So all that being said, some definitions. Jordan.
Can other substances be reacting together? So
They could. They could. They could, and then they're going to react like an acid base. We're going to actually look at that. Okay, now the top part of this next slide, you really don't need to write down. I'll leave it up. The bottom part's going to be key, but this, I think, is what you just asked, Jordan. But if we take water plus water, this is called auto-ionization. And usually those are weak acids and weak bases, which means they can act as both an acid or a base. But this is what it produces, and there's 2 ways to look at this. But again, what's up here on the top is really not what's key on this slide. What's key is what's down here. Okay, and this is where, if you look at the formula sheet, and I have you do this all the time, seems like if we went through our class. But if you look down here where it says equilibrium on the front, about a little more than halfway, there's this equation. And this is temperature specific, just like equilibrium was in the last chapter. So this is what's key right here. And again, this is on the formula sheet. Now, what's on the bottom here? You might want to write this in over to the side if you care to. And hopefully it makes sense that if the H plus is greater than the OH, it's acidic. If the OH is greater than the H plus, it's basic. And if they're equal, it's neutral. And the reason they call it KW, W, is it's just for water. So again, you don't have to memorize this. Again, this is something in first year chem we definitely dealt with. And it's not a difficult, you'll see, we're going to do some problems with it. So again, if you wanted to write that down on the formula sheet, you can, which again is something hopefully you would just have, you would get that. If the H plus is bigger than the OH, it would be acidic. If the OH is greater than the H plus, it would be basic. If they're equal, it would be. So what that really means is, if we know H plus or OH, if we know one, we can always find the other. Can I give, right, like I said, making sure you heard me. So if you look right on the formula sheet, the good news is I only have to wear this stupid mask one more day, Thursday. I don't have to wear it anymore. It's right here. So equilibrium, there it is right there, KW. So again, nothing that you got to remember. So some, I think, easy problems to do then. So here's one. Again, it'll kind of be good, I think, for the last, again, we got maybe another 15 minutes or so, and then we'll be done. But to have your calculator out. Not that these are difficult things to do on your calculator, but just to make sure. Okay, so problem is 1 times 10 to the negative 5th OH, is this acidic or basic? So to do this one, I'm going to again use this. And again, if we know one of these, we can always figure out the other. Okay, so if I know the OH is 1 times 10 to the negative 5th, so I'll plug that in. I'm going to solve for the H plus, and then I'll use this here. Then I'll compare the H plus to the OH. So just plug in the OH. And this, again, where it's not a difficult thing, but it would be worth doing this on your calculator. So again, 1 second exponent negative 14 divided by 1 second exponent negative 5. So what I get here for the H plus is 1 times 10 to the negative 9. Did anybody else get that? Okay, now I'm going to answer the question. Is this acidic, basic, or is it neutral? So here's the OH. Here's the H plus. Which is bigger? Which is bigger? You got to look at the negative. It's negative 5. OH is negative 5. H plus is negative 9. Negative 5 is bigger than negative 9, right? This solution would be basic. Because the OH is bigger than the H plus. Okay, here's the next one. Let's actually do both of these. Okay, this time we're told that the H plus is 10.0. Acidic, basic, or neutral. And then let's just do OH. What's the OH? Okay, so take a minute and try that. Again, I don't think it's too difficult. It's truly a plug and chug equation. So again, I'm using the same equation. So I have 1 times 10 to the negative 14. This time we're told that the H plus is 10. So if I solve for X, the OH, so the question, the OH, I get 1 times 10 to the negative 15th. Did anybody else get this? Acidic, basic, or neutral? This one is very acidic. You're right, Carson. The H plus is way bigger than the OH, so it's very, very acidic. Okay, so here we go back to that term auto-ionize. Auto-ionize. So that means when something reacts with itself. So we did that with water. We talked about water. We took H2O plus H2O is going to make H3O and OH. But here, NH3 plus NH3. So this is, I think you asked this question, Jordan, about 5-10 minutes ago. So one of these ammonia is going to give up an H and one's going to accept an H. And again, not by any stretch in a major point in this chapter. This up here is major point. But the term auto-ionize is when something combines with itself.
Or auto-ionize always a double arrow? Or can
It should always be a double arrow. Okay, so here, now look at this one. There was actually a question like this on the test that you guys took last week. I'll let you think about this, okay, for a second. So now it's 60 degrees. So this up here is a 25. And what 25 is typically a warm room conditions is kind of what it is. The 60 degrees is much warmer. The KW is this. So the KWs went up. Okay, see if you can do that. So remember, it's products over reactants. So the value for K, this is at 25 degrees Celsius. So when it goes up to 60, the K goes up. So remember, this is really a Le Chatelier problem. Increase, add, away. Okay, well, if the K values went up, that means the products have went up and the reactants have went down, right? Is this endo or exothermic? This is endothermic. Because increase, add, away, this is going to the right, making more products and reactants. So the energy must be on the left. It must be endothermic, and it's shifting away from there. Okay, then if I calculate the H3O, so in this case, if the KW is 1 times 10 to the negative 13, it is equal to the H3O. And remember, H3O and H plus are interchangeable times the OH. Well, if the solution is neutral, it's not saying there's more of one than the other. These are both X. So if I have X times X, is that 2X or X squared? That's X squared, right? So I have X squared. So I take the square root. And what I get for X, which is the H3O positive, is 3.2 times 10 to the negative 7. I want to do one more big topic, and then I'm going to stop. Give you guys some time to work on the lab or just decompress or text your friends. Key thing, not a hard thing, okay, on the formula sheet. Okay, the next thing is definitely a big thing. And as a matter of fact, when I was deciding, right, spring break, should we go into what we're doing now, or should we go into thermodynamics and electrochemistry, which I'm hoping we can get through a lot of that. And we'll just have to see. Both are definitely going to be well represented on the test, but I thought pH is something that is absolutely going to be on the AP test. And I think the thermodynamics, delta G and E0 will be too, and I'm going to try and get to that as well. But the pH scale. And so years ago, biologists who are brilliant, but they're not mathematical that much. And so they got sick of dealing with 10 to the negative 14, 10 to the negative 9, 10 to the negative 5th. They go, give us whole numbers. And so they came up with the pH scale. Okay, and this is also on the formula sheet, and it's a really easy calculation. And in first year chem, when I teach this, I always tell them it's a calculator exercise. And so I want to go through this in the next 10, 15 minutes, and then I'll quit talking. I keep saying I'll quit talking, but I will quit talking. If you guys have time, if you have questions on the lab, I'll be more than happy to answer. Those equations are important. And those equations, again, are on the formula sheet. So if you look back on the front of the formula sheet, on the equilibrium, there was KW, well, right under there was pH and POH, and how pH is connected to POH. And I want to show you too, because I do tutor students in normal years from other schools, Rock Canyon and Mountain Vista, Douglas County, and Arapahoe. And I have shown them this little, because I always do it this time of year. It's about when baseball season starts. So I do it in the form of a baseball diamond. It's so depressing to be a baseball fan in Colorado. It's just pathetic. It's pitiful. At least, the Nuggets, I think that new guy might be good. He's pretty good. They're trying to win. I mean, they may not beat the Lakers, who they'll go by like the old Michael Jordan movie, Space Jam. They'll go by whoever it is, so they can win. But at least the Nuggets are trying. The Avalanche are certainly trying, right? Lexi, they're trying. They're probably good. They have a chance to win the whole thing. The Broncos don't know what they're doing, but at least they're trying. But the Rockies they don't care. It's like they just want you to go down and buy some popcorn and watch them lose 10-2. They don't really care. But this came up from, again, biologists wanted to have whole numbers. And so here came pH. And what P means the negative log. If you see P, it means negative log. So when you see P, like something we're not going to get to in chapter 15 is pKa. pKa. Well, what's that mean? It means the negative log of the Ka. That's what P means. Another thing on sig figs here is when you use this, because it's a logarithm, and I don't know why, but I'm just telling you what the rule is when you use a logarithm, the sig figs start at the decimal. And I'll show you that when I do this. But when you're using a logarithm, the sig figs start at the decimal. Huh?
It's just a log base 10.
That's what it is. Yeah. And it's really going to be, we'll do it on our calculator. But what we've got here is we've got H plus. So here's my second base. We've got OH over here on first base. I don't even know who plays first base or second base for the Rockies. I used to know these things. The Rockies at one time, they had DJ LeMahieu play second base. He was like the MVP of the American. They had Nolan Arenado play third base. He'll be the MVP of the National League. Trevor Story, who they'll trade in July, he's the shortstop. Remember these guys? They used to play for the Rockies.
Wait, so if the answer you got from like this equation is like 0.003, that would be 3 sig figs just for this?
Yeah, let me do some and I'll show you, Liza. I'll show you. But if I connect these, again, so it kind of looks like a baseball diamond, home first, second, third. The way these are connected is what I was just talking about. So this is connected by KW is equal to 1 times 10 to the negative 14 times H plus times OH. You guys probably don't need this. But again, because last spring was so weird, this is something I do in my regular chem classes, and I do when I tutor students on this. So if I want to go to the H plus to the OH, this is truly how you're going to do this on your calculator. You're going to go negative log and then number. And Liza, I'll show you. I'll show you what I'm talking about. The same thing if we're going from OH to POH. So POH would be the negative log of the OH. I would go negative log of the OH. Now, these are connected by 14. So pH plus POH equals 14. So if the POH is 8, then the pH would be 14 minus 8, it would be 6. Now, if we go this way, so if we're going, so say we know the pH, and we're trying to find the P or the H plus, I go second log negative in the number. So what I mean by that is I go second log negative in the number, and I'll do that today. And Liza's question is a really good question. I want to try and answer that with sig figs. The same thing here. So I do second log negative in the number. So if I have the POH, to go to the pH. Okay, so the whole thing about pH is just to kind of simplify how acidic and basic things are. Okay, so let's do some of these. So number one. So we really have 4 things here. We have OH, H plus, pH, and POH, and how they're connected. Okay, so we're told a solution is 1 times 10 to the negative 9th H3O, which again, H3O and H plus are interchangeable. Determine, or we're trying to find the pH. So we're just going to go from here to here. And this is where you should do this on your calculator just to make sure. You're going to go negative log, and then the number 1 times 10 to the negative 9. So I went negative log 1.00 second exponent negative 9. And what I get here is, and then I'm going to go to Liza's question. So the pH, what it says on my calculator screen is 9. Okay. Now the sig figs. So what I'm saying is when we do the logarithm, so the pH and the POH, the sig figs start at the decimal. Well, this number here has 3 sig figs. This number, technically, because it's a logarithm, the sig figs start at the decimal. And so I have to do 3 zeros. Okay, so
Basically, what you're saying is if we have one of those 4 values, we can do a 2-step problem to find the penny.
yeah. Sometimes you can do 1 step like that. Okay, here's number 2. Take a second, see if you can do it. Again, it's something that you guys can probably manage. We're given the OH, and to George's point, he's exactly right. So the H plus, the pH, the POH, and it really doesn't matter if you go first to second to third to home, or you could go home to third to second. It doesn't matter which way you go. Do our best to watch the sig figs too here as we go. Okay, so to go from OH to H plus, I'm going to use 1 times 10 to the negative 14. So 1 times 10 to the negative 14 divided by 2.8 times 10 to the negative 6 to 2 sig figs, 3.6 times 10 to the negative 9. Okay, now to find the pH, so I'm going to do the negative log of that number. pH is about the H plus, so the negative log of 3.6 times 10 to the negative 9. This is where I got to watch sig figs. Again, when I do the logarithm, the sig figs start at the decimal. This has 2 sig figs, so that 8 is not considered significant, so it'd be 8.44. Okay, and then the POH, I would just do 14 is equal to pH plus POH. So it's 14 plus 8.44 plus X. So I'll just subtract. So I have 14 minus 8.44 gives me 5.56. So you're right. It's kind of like if you know one, you know all of them. Okay. So Coke, I got my Diet Coke out here right now. pH is 3.2. Calculate the H plus. So that means this time we're going this way. So Liza asked a really good question just a few minutes ago. 3.2, because this is a logarithm, how many sig figs does that have? It has 1. Because remember when we do logarithms, so pH and POH, the sig figs start at the decimal. This has 1 sig fig. So go second log negative 3.2. And this is what it shows on my screen on my calculator. For the H plus, it shows 6.31 times 10 to the negative 4. But technically, I should have 1 sig fig. So it'd be 6 times 10 to the negative 4. Did anybody else get that? You did, okay. Okay, almost done, truly almost done. Okay, how much more acidic is Coke than neutral water? So what I'm going to do is a ratio. I'm going to divide the H plus of Coke over the H plus of water. Do Coke over water. Well, Coke I just found, the H plus was 6 times 10 to the negative 4. And water I know is 1 times 10 to the negative 7. So that's 6,000 times more acidic. Technically the rule is for a difference of 1 in pH, a difference of 1 is 10 times stronger. So a difference of 2 is 100 times stronger, 3 is 1,000 times stronger. Okay, let me put up this next slide real quick, and then I want to go one other thing, and then I'm going to quit, like I said. Let me put this up. I'm going to come back to this. Let me just, and I'll leave this up. But here are the meaning of pH, the meaning of the numbers. Okay, and note what this says, okay? You can really make this more concise. On the top is pH, on the bottom is POH. It's kind of like Jordan said, if you know one, you know the other. The pH of 7 is neutral. pH of 7 is neutral. Less than 7 is acidic, and the smaller the number, the more acidic it is. And greater than 7 is basic, and the larger the number, the more basic it is. Okay, and I'm going to come back to that slide and just leave it up for those that want to copy down. But let me just real quick, the next slide will be a perfect place to stop. Here are just the pH of normal household things. So pure water, blood, and this is something in chapter 15, which we won't get to, but it's really fascinating to look at the chemistry of blood. And it's something that we would understand, but it's just barely basic. Where milk is barely acidic. Okay, and here's vinegar, lemon juice, stomach acid. Now we just talked about Coke. So again, things that we ingest, we eat or drink, those are acidic. But up here, ammonia, household cleaner, sodium hydroxide, again, a cleaner, they are basic. So, and here's our 1 molar, so really not too concentrated HCl. Here's some problems again that you guys can be looking at. Okay. You guys did good. That was a long haul, but we did good. I'll leave that up. I'm done. The rest of the period is yours, so we have about not quite 20 minutes. I'll come around if you have any questions that you want to go over on the lab. I'm more than happy to help answer those questions. John.
I was doing the pre-lab for the lab on Thursday, and I got stuck on number 5.
Okay, now first of all, in this one, whenever you have an acid plus a compound with CO3 or HCO3, it's always going to give off water. It's always going to give off a salt, so the NaNO3. Plus it'll give off CO2. So the pH, so what I would do if it's 0.150 molar sodium hydroxide, because that's a strong base, it would be 0.15 molar hydroxide. So then I would use this.
Got
And
it.
we can check it. Perfect, Brooks. Just go ahead and put them right back there. Got it. Thanks, brother. Sure, and Joan, I'm happy to check it with you when you get it.
Are you a betting man? Oh, yeah. Am I going to Vegas?
Oh, I do like
Lexi, I'm hearing 4,000 people to go to your house.
I'm sure it's a good server.
When are you gonna go here next month?
Real familiar, doesn't it? Real familiar, doesn't it? Oh, because you're.
Something's gotta be made right.
So exactly.
Earlier, like when they started having babies, a lot of times I feel like give me the first opportunity.
So why did the color change? Because what does it put?
It seems like I've lost.
You're talking about the color one?
Yeah.
Right? Wait.
It works. There's nothing they can do about it.
Thank you.
Jonah, what'd you get?
13.177.
I don't like it. I like it.
I'm gonna run to the bathroom.
That is fine. That's what I have. Good job. Yes.
Right here.
These two that I have right here.
Can I take a picture?
That's it.
Yeah, we don't do solar on it.
Three types of stresses that can
You're going to win this. You're going to win this. You don't have a choice.
I'm gonna put a trash can.
This is explain the shot here. And then explain the showering.
Mr. Wood, can I use the bathroom?
You bet. Is there a pass hanging there just to the left of the wall?
No, I think Tyler.
Just go, just go.
And then I'm gonna say each one.
I just want to make sure because I don't have a real calculator.
Yeah.
Is that right?
I was wondering.
You're welcome to use this too, Rex. I think that is. Yep, that is exactly right.
Okay, thanks.
If you want to use it, just feel free. Just
Yeah.
put it back.
Thanks.